Thank you for the introduction, and also I need to thank the ICBC to give us this opportunity to give a talk, and especially for the award of this paper. And as you see, the slides is made by DeMarco because she's supposed to be here, and but saying something happened, and she has to cancel the flight like a few days before the ceremony. And as she already made the slides, and it makes me much easier. I just use her slides. This is the paper. So I'm going to talk about the uniform Manin-Mumford for a family of genus 2 curves, and the DeMarco and Krieger are the co-authors. So because this is communal algebra and algebra geometry, let's say something about the dynamics and the arithmetic geometry. So complex dynamics is the one study the dynamics with the complex structure. For example, the most study one is the one that study the polynomial of the P1, which is the rational function of the P1. And especially like the complex dynamics is about 100 years ago. So people start to study complex dynamics, and especially in 1980s. So the developer of the computer science. So people can see the picture of the dynamics. For example, you can see the Mumford set, right? You can see the Judas set, all these kind of things. And people realize that okay, there are lots of the things that are very interesting. And later one is to start from a complex analysis point of view. People study the topology of the Mumford set and the connectivity of the Mumford set and the structure of the Judas set, all these kind of things. And later on, people try to combine the dynamics. So because the dynamics you can study the polynomial dynamics so the polynomial dynamics on P1 is the rational function, and that is algebra, right? So you can also study the arithmetic property of the dynamics. So you can combine the dynamics and the arithmetic geometry. And the thing is that so there is a connection between the dynamics of P1 and the arithmetic geometry of the elliptic curves. So especially there is a connection called the lattice map. The lattice map is a map from P1, and that is the reduced map of the multiplication by n map on the elliptic curve. So then you can, from the dynamics of the polynomial, you can, especially from the lattice map, the dynamics of the lattice map, you can study the geometry and the arithmetic of the elliptic curve. And also our paper we can study from the arithmetic of the elliptic curve, and you can study the genus 2 curve in the Jacobian. Lattice map is the one that is the one look, for example, this one elliptic curve you multiply by 2, and this one you p and minus p in the involution you maybe to P1, right? And yeah, it goes upward. But the thing is that we study property here, and we can understand the property here.
I see.
Okay. Okay, and then from this one we can get the arithmetic geometry of the genus 2 curve. Okay, so let's just introduce some of the very simple dynamics. So the polynomial, quadratic polynomial, for each c, so you have a dynamics from the c to c. It's a polynomial, right? It looks very easy. But since the dynamics of this one is really not very easy. So let's see. So we studied the orbits of the point on the complex plane, right? So if you are given any C, so you get a dynamics, and from here you get a Z naught. You study the orbit of this one, and the iteration of the F you denote by Fn. This is not a multiplication, and the point is periodic if the orbit is. If this one is periodic, so some iteration of the Z naught is going to get back to itself, and a point is preperiodic if its orbit is finite. So you can imagine that this is the most easiest point, right, in the dynamics, right, because it has the it has finite formal orbit, and then this is very important in dynamics too. This is the multiple set, right? You see all the multiple set everywhere, right, especially in math. And what is this multiple set? In dynamics, the multiple set came from this family. This is the primitive space of this family of dynamics. And what is this one? This one, the multiple set is the one that the Krieger point. So for the Krieger point of this one is Z equals 0, right? The Krieger point, the unique Krieger point, the forward orbit of the unique Krieger point is bounded. And this is the multiple set. And which means the dynamic Krieger point is bounded. And there are infinitely many of the periodic and the preperiodic points. So for each C, there are infinitely many of the periodic point and the preperiodic point. So for example, if you fix C and then you can find the solution of this polynomial. So this is the polynomial, right? Polynomial is C with integer coefficient. You can imagine that you will have lots of solutions, right? And also, so the boundary of the multiple set is what? You can imagine that. So the critical point, is 0 is preperiodic. It stands on the boundary of the multiple set. So you can see for there are lots of the C on the boundary of the multiple set such that the critical point 0 is preperiodic. Okay, so this is the picture, and also let's see some examples. So the thing is that the period point are dense on the boundary of the field Julia set. What is the field Julia set? The field Julia set is the one that the orbit of the dynamics, the orbit of the point is not going to infinity. Okay, this is the field Julia set. Field Julia set is the point such that under iteration, so the orbit won't go to infinity. And the boundary of the field Julia set is the Julia set. And the factor is that all the period, the Julia set, which is the boundary of the field Julia set. So you will have the dense set of the period point here. For example, let's see C equals 0, right? C equals 0, the dynamics is very simple, right? So any point Z go to Z square. And you can imagine that if the absolute value of Z is bigger than 1, the iteration go to infinity, right? If the absolute value of the Z is less than 1, it will shrink to here, right? So and the only thing that is not stable is on the unit circle, right? So you can imagine that if you have some perturbation here, right, you go to infinity. If you have some perturbation here, you go to 0, right? If you stay on the unit circle, it kind of is expanding. And what is the pre-period point here? Is the root of unity, right? So root of unity. So you can imagine that root of unity is dense here on the unit circle, and there are another two pre-period points. One is 0, right? 0 is fixed, and also infinity is fixed. So that's it for Z square. So the set of the root of unity and the 0 and infinity. And also, so if C is equal to minus 0.2, so you can imagine that this one is so this one, the boundary of this one is a quasi circle, and yeah, the dynamics on here on the boundary is topologically is the same of this one. But the sense that if you keep changing the C, you will see more complicated dynamics. Okay. So essentially, even though this is the easiest family of the polynomial, the dynamics is very complicated. Okay, so this is the airplane, right? And this is the thing. You will see lots of the complicated thing. And also, this is so this is a very very beautiful picture. And also this one, and this one is a contour set. So if you keep changing the C, you will have more and more complicated structure of the Julia set. And you know that the prepare point is dense on the Julia set. So you can imagine that there are lots of the prepare point.
Is it connected?
This one is not. This one is totally disconnected. Yeah, because this is a contour set. Yeah, but I think it's
Pretty small value for it to be connected.
Let me see. 0.4, I think it's 0.25. 104 is the one on the boundary of the multiple set, I think. So this one is bigger than so this point is outside of the multiple set. Okay. And also you see lots of the very complicated structure of the Julia set. And in complex dynamics, the topology of this one and of this kind of things has been studied for a long time. And for example, people study whether the Julia set has positive Lebesgue measure or not. And the answer is yes. You do can find some this kind of polynomial, such as the Julia set. Julia set is the boundary of the field Julia set. Has major positive measure, Lebesgue measure. I'm not quite sure it's totally connected or not. Probably not. But probably not. But you can find some of them. I didn't say it can be. I'm not quite sure, but I think it shouldn't be totally disconnected.
I thought she should prove from the.
But the things that you can imagine that, for example, in Z squared plus C, right? So the things that if the C is outside the multiple set, you can imagine that it shouldn't be very complicated, the Julia set.
When does it become disconnected, you said?
No. So you see the multiple set, right? So this is the parameter space of and for the point outside of the multiple set is totally disconnected. And for the point on the multiple set is connected. And the main conjecture of the complex dynamics to study the MLC, multiple set is locally connected. So this one is still open. Some basic question is to what extent do this set of prepare point distinguish the different polynomials, right? So for any polynomial, like you have a set of prepare point, right? And the thing is that can we use this set to determine the polynomial, or can we use a subset of this one to determine the polynomial? So. Okay, we mean a set means we forget about the periods and we forget about the orbital length. So we just remember the geometry configuration of the points. Okay. So there is a basic fact by Baker and DeMarco, like a few decades ago. So the set of prepare point for FC1, FC2 coincide if and only if C1 equals C2. So essentially, the set of prepare point to determine the dynamics, right? Okay, so this is a few decades ago. People know this one, and then the next next question is how many common prepare point can FC1 and FC2 have if C1 not equal to C2? Okay, so how many points you need to determine the dynamics? Okay, for example, this one, right? So this is c equal to 0. So you know the set of prepare point is the root unity and 0 and infinity, right? And also for c equal to -1, so because you know this is the field Julia set, the boundary is the Julia set, and you know the set of prepare point is based on the Julia set. So you know there are lots of them, and you can see that. So for the field Julia set, right? Or for the Julia set, you see there are lots of overlap, right? The Julia set cannot the intersection of the Julia set cannot determine the dynamics, right? So you see, right? So this one corresponds to c equal to 0, and the other one corresponds to c equal to -1, and you will see that the Julia set has lots of intersection, right? So this is the zoom in. I think this is zoom in somewhere. Yeah, somewhere here or some. Yeah, I think it should be somewhere here. Yeah, you can see lots of intersection here. Lots of intersection here. Right? You can imagine that there are lots of intersection for the Julia set. So, but the thing is that the Julia set is, the prepare point set is dense in the Julia set, but the sense that it has more information here. So this one is the c equal to -1.5 and -1.9. So you have like two Julia set, right? So you can imagine that a Julia set somehow can have lots of might have lots of intersection. And so the next result is by Baker DeMarco, and also independently by Yuan and Zhang, like about 10 years ago, 1 decade ago. And it says what? It says that for C1 not equal to C2, the polynomials FC1 and FC2 have only finite many of the common prepare point. So the previous result is that for C1 and C2 not equal, right? Then these two sets, the set of prepare point of FC1 and FC2 are different, right? But it doesn't say that they cannot have infinitely many intersections, right? But this result says that okay, if C1 not equal to C2, then in the intersection of these two infinitely many points can only have finite many points. Unfortunately, no. But later on I was.
Examples of C1 and C2?
Yeah, definitely. we will have example later on. They will have like probably like 27 points. We will see it later on. Yeah, so the thing is how many common prepare points can F and FC1 and FC2 have if C1 not equal to C2? Right. This one says they can only have finite many of the overlap, right? So the question is how many? Is there any uniform bound for this one? Right. So for example, if you think about this example, right? C1 equal to 0 and C2 equal to -1. So how many overlap for the prepare point set? The thing is that. So you see there is 1 point here, this is 1 point here, this is 1 point here. At least you can see 3 of them, right? Can we have more? The answer is, so you didn't see anything here, right? Well, probably there might be something there, but the thing is that, in fact, there are, these 3 are the only point. They overlap. These 3 points are the common prepare point for these two dynamics, but they are all. They cannot be more. So why? So because they are all integers, right? So they're all integers, and then you know that all the prepare points for these two dynamics for the intersection point is Galois invariant over Q, and then you know that there are only 3 of them, right? So you cannot have more points. That is Galois invariant. They're still in the intersection of the two Julia sets, right? So why? Because, for example, if you have a point here, right? Because the prepare point for this square is the root unity, right? And the Galois orbit of this one is definitely has something here, right?
What is the Galois?
The Galois group is the over Q bar over Q.
Oh,
the Galois orbit of the point is called Q bar over Q. Because everything, because this one integer, right? This is integer, right? So the set of points is, yeah. So this is an example to show, okay, so this example, there are only 3 of them. You cannot have more. Okay, so the idea for Baker and DeMarco to prove this one, because this slide is made from Lola DeMarco, so she wants to talk about something about her result. The idea of the proof is the first assume C1 and C2 are algebraic, right? And so C1 and C2 are roots of polynomials equations with integer coefficients. And then the sense that the set of the common preperiodic point must be Galois invariant over this field, right? Over this field and a field of finite extension of finite degree over Q, and at least if this set is infinite, so then it must uniformly distribute on the Julia set for C1 and C2. And a long time ago, so we already mentioned that if for these 2 polynomials, if the Julia set is the same, then the parameters, they should be the same polynomial. Okay. So the idea is that if they are infinitely many overlap, then they will equidistribute to the Julia set for both C1 and C2. And if the Julia set is the same for this dynamics, the C1 must be C2. So there is another case, either C1 or C2 is not algebraic, then you need to use the equidistribution take place on the Bokovich analytic space instead of the C. So you need to work on the function field. You need to work on, you can view this one, for example, this one is transcendental. So you need to work on the field Q bar generalized by C1, right? Some field here. And so for this one, like distribution sense, you need to use some work by Baker, Chamberlain, and Favre, and River, Latier, and Romney, and exploring the global property of the K. So because you want to get the distribution sense, you need to study of all the place of the number field. So you need to study Archimedean one and a periodic one. And so this one step is the main point of the article is you need to how to treat the one that so C1 or C2 is not algebraic. You need to go to the function field and use the Bokovich space, and you also use the equidistribution sense. You need to some argument to say okay C1 still equal to C2 if they have infinite many overlap. I don't think this one uses specialization, may not use the specialization to get this one partial sense out. So the next work we do use the specialization. But this one probably not use the specialization. Or maybe can use the specialization, but at that time, they do not use the specialization. Okay, so the answer for this question is, okay, there is a uniform bound of M such that FC1 and FC2 have at most M common preperiodic point when C1 equal to C2. So essentially it means that you can find the finite many of the point. It will determine the dynamics of the FC, right? So the key idea in the proof is the quantitative arithmetic equidistribution sense. We use the result of Favre and the River here. Yeah, good question. It shouldn't be that big. It shouldn't be that big. So I remember in the ICM talk, I saw Lola said she believed not probably not bigger than 10. And later on we saw some example is 27. I think it's 27. Yeah. So we believe it's probably not bigger than 100. So this is the effective bound, right? So at the beginning we don't get this bound, and I think so we think we can get a bound, and I said okay, probably it shouldn't be bigger than it shouldn't be too big, right? It shouldn't be bigger than 17 million, right? I mean the twin prime, the first result twin prime. It's not. So we can do it for ZD plus C, the same thing. Yeah, so for example, if this one is z equal to 3, 4, probably you need to change this one a little bit.
Yeah. Actually, that's my question. Why just quantile? I don't work on this thing. Why just quantile?
Because this is the easiest one, and this has lots of interesting things already here.
There are already many features available.
Yeah. It's kind of it's somehow important, but I don't think that one is the crucial thing. But because you only have one parameter, right? If you only have one parameter, lots of things you can compute. No, I don't think so. So essentially, later on, people can do it by using other technique. So people can do other family. Okay, so essentially, we get this one very big is because in one estimate, because we say that something is continuous and we want to get some bound, we get a very, very small bound. So only one step, we get a very big, very small thing, and it makes this big. For other computation is kind of really small. Only one step, we get a very, very terrible estimate. Okay, so the main result of our paper is this one. So let X be any compact Riemann surface in genus 2. In genus 2, let the degree 2 map to an elliptic curve. And then we embed this one by a hyperelliptic embedding. And there is a uniform M independent of the choice of X, such that this one is the X inside is Jacobian. And the torsion point is uniformly bounded by M. So you can imagine that you have this one, you embed this in Jacobian, and this curve intersect the torsion point of the Jacobian is finite in uniform bounding above. Okay, this is our main result of the paper.
This is the Manin-Mumford.
Yeah, this is Manin-Mumford. A case of Manin-Mumford. So because Manin-Mumford says, okay, for any curve, right, and it's Jacobian, and the torsion, if the genus is greater to the torsion point is finite, right? So this is the uniform version of the Manin-Mumford. Okay, so here's something. So essentially, what is the one what are the curves satisfy this condition? It's a family of curve, right? So it's a two complex dimension of family of Riemann surface of genus 2. And also the point is that the finiteness for each given X was the Manin-Mumford conjecture that is proved by Reynolds, like a few decades ago. And then later on, the Marin asked if the bound depends only on the genus. This is the result of the uniform Manin-Mumford asked by Marin. And okay, so more recently, like a few years ago, the Kuhl completed a proof of the four uniformity conjecture for all X, all genus, and all embeddings. So it builds on the work of the Demeter, Gao, and Habeck, and the height bound, and also the arithmetic degenerations for family of the abelian varieties. And the further proof have appeared by lots of authors, and also independent by Hexi Ye. What I heard from Hexi Ye is that his proof is kind of different from this approach. So any question? Okay, so what is the connection between the dynamics and the uniform Manin-Mumford? So here's the thing. So for example, so you have, for example, if you take a elliptical, right? So you can have the multiplication by 2 map. For P, you map P to P, right? So you get some action here, and then you self map, then you get a dynamics here. And if P is torsion, means that n times p equals 0, right, for some n. And also that p is preperiodic if for phi if its orbit is finite. So what's the connection of the torsion and the preperiodic? So the thing is that p is torsion if and only if this one is preperiodic under the multiplication by 2 action, and if only if the projection of the elliptic curve to the P1. What's the projection? So you just take the involution, P and the minus P, you map it 2 points into 1 point and you get a P1. And if and only if the projection here is preperiodic for some F5, F5 is the induced map of the multiplication by 2 map from the elliptic curve to the P1. So this is the connection between the torsion and the dynamics. So it's especially we look at we look on the general family of the elliptic curve, right? And the sense that if you project this one from the elliptic curve to the x coordinate, and this multiplication by 2 map, the phi, it will reduce to this lattice map. This is the lattice map on the P1. So you can imagine that this one here, under the multiplication by 2 map, you have finite orbit, right? You can, because this one is degree 2 map, right? So you can imagine that this one also have finite orbit, right? So this one is preperiodic here, if and only if the projection here is preperiodic, and if and only if here is a torsion, right? So you connect the torsion point to the preperiodic point. And the conjecture by Bogomolov and Chinko, like in 2007, and Bogomolov, Chinko by 2000, a few years ago. The conjecture is there is a uniform bound M such that the lattice map, at least for any 2 lattice map, FT1 and FT2, given by this one, have at most M common preperiodic point whenever the T1 and the T2 are not equal. So this is the same flavor from the same flavor as the dynamics of the z squared plus c, right? That one is the family of quadratic polynomial. This one is the family of rational function, right? So, but this one, the good thing is that that one is the z squared plus c is the easiest sense you can see from the dynamics. This one looks a little complicated, but the sense it came from an elliptic curve, right? Elliptic curve has group structure, right? So you can imagine that this one is also very special one, and it's kind of you have some group structure here because it came from a group action. Okay, so the torsion point definitely is dense here, right? And then the period point is dense on P1. Yeah, you can imagine that they are dense here. And the finiteness of the pair. So for C1 not equal to C2, T1 not equal to T2, there are only finite many of them. Then is first observed by Bogomolov and Chinko. And this is the corollary of Reynolds theory, the uniform Manin-Mumford. And the other proof of finiteness follows from the experiments of Becker, DeMarco, and Yuan and Zhang. So by just looking at the overlap of the common preperiodic point. And this one is the t value such that x equal to 2 is preperiodic, is prefixed by f. So you can see that there are lots of the t, right? They have common preperiodic, right? Because for any t here, this is a t, this is another t, this is another t. So x equal to 2 is fixed, right? So it means that for all this t, the common preperiodic point at least 1 point, right? 2, right? Uh-huh.
Can you tell me how we get the quadratic polynomial? The original one.
No.
Portion over there, I want to get 3pr.
No, you cannot get.
No. How do you relate it to something?
The thing is that the quadratic polynomial, right? So it's a family of rational function, and the lattice map is another family of rational function. And then we studied the same thing, the common preperiodic point.
Okay, but how do you determine it?
The techniques are the same. Yeah. And especially in the complex dynamics, the lattice map, people don't know study much because you didn't see lots of the topology sense here because everything is the Julia set is everything, right? And the major is kind of smooth. You do not see the very complicated topology here. But the sense, if you study the arithmetic, you have the connection with the elliptic curve. You have lots of those things. Okay, so what is so the things that the uniformity. So they already know the finiteness of the if T1 not equal to T2, right? There are only finite many of them, but the uniformity is much harder. Okay, those things that okay, this is the connection. So they study the same, almost the same thing, but the technique is the same. The technique is similar, and they are the same problem for two different family. Right. The same problem, the same flavor problem for two family. Yeah. So the conjecture is you can do for any family, but we can only do two of them. Okay, so the thing is that the conjecture, we prove the result, and then we get the conjecture. We prove the conjecture here. Okay, so how does this one lead to rejected? So this is you start a common point of a family of dynamics, right? And this one you study the uniform Manin-Mumford. How does this one rejected? So you just go from here. So essentially, if you study this is P1, right? You have the FT1 dynamics here, you have the FT1 dynamics here, and then you have the ET1, ET2, and you can. So the common prepare point is on the diagonal, right? So on this dynamics. So the prepare point of this dynamics, the first coordinate and second coordinate, and then what is the torsion point of this? Leads abelian variety is both of them are torsion, right? So then you can lift this one the diagonal. You start a common prepare the diagonal, and then you lift here, you get a curve, and then this curve you normalize this one, you get a genus 2. A genus 2 curve. And if you embed a Jacobian, then you have the isogeny from a Jacobian to here. And if you understand the sense here, then you understand the torsion point. So that's the connection. And yeah. And then what is the number? The Pullman, like in 2000, found examples with essentially. So he found lots of infinite many curves, such that the torsion point, the curve have like more than 22, at least 22 torsion points. And Michael Stoll like found an example like this is 34. And they said, what's the record for the Z squared plus C? Is this one? So you have like this one. This is the F. This is G, right? And the common pre-point is at least. Yeah. I think it's 27, right? Yeah, it's 27. So you have lots of. So we believe it shouldn't be very big. Shouldn't be like 1082. It should be probably this might be the best example because this is the record we have. So people have. 26. You need to count infinity.
Oh.
I think it should be because uniformity is defined for everywhere. The M is defined for every C, right? C or yeah, it's a record. You can imagine the simplest one should have the most intersection. Okay, so the thing is that the conjecture is that is there any uniform bond such that for any any pair of the map of the same degree? If the period point is not the same. So we have two families, right? One family is the two easiest families, but the conjecture is that okay for all the rational function on P1, they should have this kind of sense. And the more general conjecture is is this one made by DeMarco and also Malarkey, and for family of the a family of dynamics on P1 on Pn. So this is a more general conjecture, and this conjecture is kind of very open. It's very open here, but the sense some of the things knowing here is in the case of abelian varieties, and this one is proved by Gao and Habecker. And this conjecture is a generalization of the Wu Zhang's dynamic Manin-Mumford conjecture. It contains lots of the unlikely intersection phenomena in this conjecture. Yeah, in the case of abelian scheme has been proved by Gao and Habecker. But you can imagine that abelian variety, you have the dynamics, right? You have the multiplication by n, something like that, and you have dynamics.
The higher dimension, I don't know.
Yeah, definitely. Mm-hmm. And yeah, and more general, not only the intersection of the things. You can study the parameter space, all these kind of things. Okay, thank you for listening.
I'm not exactly sure how to phrase this, but there should also be a stability result, right? That if two polynomials, if the set of periodic points of polynomials is close in some sense, then the polynomials.
Yeah, so essentially we prove the uniformity is that they cannot be close. The set of people cannot be close. You can imagine that. You can imagine that for algebraic number, right, they can never close. Why? Because of the product formula. Because of the product formula. In some place, in Archimedean place, it may close, but in some periodic place, it has to be far away from each other, right? So for any two algebraic number, they can never be close, because if it is close in some place, it is by the product formula, right? The difference of these two, the product of the norm is 1, right? So you can imagine that if the Archimedean is very close, then some non-Archimedean distance it shouldn't be close. That is the main point of our proof of the uniformity. So you can imagine that if they share lots of the prepare point, right? And then it means that the two zero set should be very close, right? And but the thing is that because they are algebraic number, right? So you can imagine that for some place, in Archimedean place, the zero set is very close. Then definitely in some other periodic place, the zero set shouldn't be very close, right? So that's the main point of the proof. Yeah, it's a very good question. Yeah.
And it has some set of preperiodic points.
Yes.
Is there a finite subset of these preperiodic points, so that if another Fc prime has preperiodic points sufficiently close to them, then they have to be closest, then CNC prime will be close, or something like this? Somehow.
Yeah. So the result says, for example, if you have enough for any choice of finite many of them. So if the number is big enough, then definitely no. So it's impossible for other polynomial to share the preperiod. I mean, you need to fix the degree. If the degree is growing, definitely you can have.
So it doesn't matter which points. I mean, just as long as enough of them are.
Right. We forget about the things. We any point. So we just control the number. We forget about the orbit length and all these kind of things. We just remember the geometry or just remember the number of those things, the minimal information you need.
More questions?